Welcome to The Explainer. I'm absolutely thrilled to have you here today. Go ahead and put on your solar physics professor hats with me because we are diving deep. We look up at the sun every single day, and it just seems like this constant, unchanging sphere of light, right? Well, actually, scratch that. Beneath that blinding surface, the sun is hiding a highly dynamic and surprisingly asymmetrical secret. Today, we're going to explore those hidden dynamics by dissecting a really fascinating new case study. We're looking at mapping the hidden currents that are literally rewriting our entire understanding of solar cycles. So, for decades, we've observed the sun's 11-year heartbeat. We all know the basics. It's a cycle where magnetic activity ramps up, sunspots appear, and eventually, the entire global magnetic field completely flips. But here is the core mystery we're tackling today. What actually dictates the timing of these magnetic cycles? And why on Earth do the sun's northern and southern poles sometimes flip completely out of sync with each other? To solve this, we can't just look at the surface. We have to go deeper. Here is our syllabus for today's explainer. We'll start with the solar cycle mystery, move on to the cycle 24 hemispheric divide, then check out currents beneath the surface, the power of plasma beta, decoding past solar cycles, and finally, predicting the sun's future. Let's jump right into part 1, the solar cycle mystery, mapping the surface. Let's pull down the chalkboard in our virtual lecture hall and look at the raw data. This beautifully complex graph is what astronomers call a magnetic butterfly diagram, tracking 14 years of solar activity. Those red and blue sweeping waves, they represent surface flux transport, which is specifically driven by what we call meridional flow. It's basically tracking how massive magnetic fields migrate from the active mid-latitudes, where the sunspots live, all the way up to the sun's poles. The arrival of this magnetic flux at the poles is absolutely crucial, because that's what actually builds up the polar field for the next cycle. But here's the catch. Looking at surface meridional flow alone just doesn't explain this strange anomalies we sometimes see. Which brings us to section 2, cycle 24 hemispheric divide, a bizarre timeline. We need to talk about the anomaly that sparked this entire investigation. The timeline of solar cycle 24 was incredibly asymmetrical. Honestly, it was genuinely bizarre. Let's dive into this direct contrast because the data here is staggering. In solar cycle 24, the northern hemisphere's polar field peak was severely delayed. It didn't reach its maximum until around 2020, right near the cycle's minimum. But the southern hemisphere? No way. It reached a premature maximum nearly 4 whole years earlier, back in 2016. Just imagine a heartbeat where the bottom chamber beats 4 years before the top chamber. Why did the south peak so early? Let's trace exactly how this played out chronologically to understand this massive lag. In 2014, something incredible happened. Flows measured beneath the active regions of the southern hemisphere reached their absolute peak. Just 2 years later, in 2016, the southern polar field accumulated its maximum flux. All the while, the northern hemisphere was dragging way behind, finally peaking in 2020. The key to this whole mystery is that 2014 event. Take a close look at the data tracking those precise movements. See that dashed red line peaking right in 2014? That indicates a powerful subsurface flow, specifically a southern outflow speeding along at about 12 meters per second. Now, right below that, check out the black dashed line representing the southern polar field. It surges and hits its peak in 2016. This brilliant tracking shows how that specific, incredibly powerful southern outflow directly drove the massive flux accumulation at the southern pole just 2 years later. Okay, section 3, currents beneath the surface, finding the smoking gun. So we know when it happened, right? But how? Well, the smoking gun hides deep in what's known as the near-surface shear layer. When we look at the near-surface layer, at 0.99 solar radii, we see a strong negative correlation between flow speed and the magnetic field. And for a long time, models assumed those converging inflows near the surface dictated flux transport. But look at the data representing a much deeper layer, down at 0.95 solar radii. Down there, we see a totally different story, a strong positive correlation. As the deeper outflow speed increases, the magnetic flux increases right alongside it. So here is the crucial takeaway. The near-surface shear layer hosts a vertically structured circulation system. You've got inflows near the top and outflows near the bottom. The near-surface inflows do not, I repeat,
do not dictate global magnetic transport, despite what earlier models suggested. The real drivers, the hidden conveyor belts of the sun, are the outflows located deep down at 0.95 solar radii. These deeper currents, which are heavily modulated by the active sunspot regions above them, cause variations in the meridional flow that ultimately drive that global magnetic flux transport all the way to the poles. Moving on to Section 4, the power of plasma beta, physics of the deep. Now, you might be wondering, how on Earth can a flow of gas, plasma, push massive, incredibly powerful magnetic fields around? The answer lies in high plasma beta. Let's define this clearly. High plasma beta is a condition deep within the sun where the kinetic energy of the moving plasma massively exceeds the local magnetic energy. Think of it like a raging, fast-moving river carrying heavy wooden logs. The logs are the magnetic fields. But because the river, the kinetic energy of the plasma, is just so powerful, it's in total control. It physically drags the magnetic fields along for the ride through a process called advection. To really put this into perspective, let's look at the sheer energy involved here. A typical 15 meter per second poleward flow at this depth of 0.95 solar radii carries a kinetic energy density of about 900 joules per cubic meter. Now, up at the surface, the magnetic fields are only about 10 to 20 Gauss. That 900 joules of kinetic energy completely, utterly overpowers those magnetic fields. The magnetic energy would literally have to be over 20 times stronger just to resist it. It is a staggering display of force. The plasma flow simply takes over, breaking up and transporting the magnetic flux wherever it goes.
Next up, Section 5, decoding past solar cycles, validating the model. As solar physicists, you know we have to test our theories against the historical record. We can't just look at one cycle. So here we have synoptic magnetograms covering solar cycles 21 all the way into the rising phase of cycle 25. And guess what? By analyzing this data, researchers found that the historical patterns perfectly align with our new flow model. The hemispheric asymmetry we saw in cycle 24 wasn't just some one-off glitch. That exact same time delay of 2 to 3 years between deeper outflows and polar field buildup is clearly visible in cycles 21 and 22 as well. Take a look at this table highlighting some specific historical anomalies that basically prove the rule. Sometimes the active regions are so asymmetrical that the deep subsurface flows cross the equator entirely. Look at the years 1984, 1993, and 2015. In each of these cycles, massive cross-equatorial flux plumes originated in the more active southern hemisphere. And in every single case, those deep outflows predicted a rapid enhancement of the polar field in that exact source hemisphere. The historical data validates the model absolutely perfectly. Finally, Section 6, predicting the sun's future beyond cycle 25. So why does mapping these deep currents actually matter to us down here on Earth? Well, it's all about real-world application. The researchers published this vital conclusion. These results identify activity-dependent flow variations in deeper layers of the near-surface shear layer as a dynamically significant component of the Babcock-Reaton process. Okay, so what does that mean in plain English? It means we can no longer model the sun's dynamo by just looking at the surface. These deep, hidden conveyor belts are a fundamental, systematic regulator of the sun's entire magnetic cycle. And honestly, that leaves us with a totally thrilling prospect. The sun's activity directly creates space weather, and that impacts our satellites, our power grids, and our global communications. If solar cycle predictability is fundamentally controlled by these deep, high plasma beta currents we've been talking about, then by mapping the hidden flows at 0.95 solar radii today, how accurately will we be able to forecast the massive solar storms of solar cycle 25 and beyond? Decoding the sun's deep currents isn't just about solving a really cool scientific mystery, it might literally be the key to protecting our modern, connected world.